All right, in today's ANSYS exercise, we're going to go over how to do explicit dynamics in ANSYS. It's going to be a little different than the other types of analyses we've done in ANSYS, and it'll tie into some of our lecture material in terms of the meshing and the setup for an explicit dynamics analysis. We're going to be using LS-Dyna, and specifically, ANSYS purchased LS-Dyna a few years ago. LS-Dyna is probably the leading explicit dynamics solver used a lot in the auto industry and other industries for doing crash type simulations. So today we're just going to do a simple simulation. This video, which I'll also put the link in the description, is a good, more advanced video in terms of some of the intricacies of doing explicit dynamics using LS-Dyna. We're just going to do a simple simulation. In particular, I'm going to be using the built-in materials. To do more advanced simulations, you have to kind of specify your material cards as kind of outlined in this video, this other video. All right, so we'll get going. We're going to download this space claim model file. And we're going to load that into the workbench window. But first I'm going to drag in an explicit dynamics, or sorry, an LS-Dyna block into the workspace. I'm going to add a model like we've done before and import geometry. We'll browse and grab this cylinder test case. All right, so this is just going to be, we'll go into setup here and I'll show you what the geometry looks like. All right, it takes a little bit for that window to open, but now it's open. So you can see the geometry I've set up here. I have a plane at the bottom. We have two surface bodies. The plane at the bottom, which we're going to use kind of as a floor to constrain the cylinder. We have the cylinder, which is hollow, and it's a surface body, and then we have the solid body is this mass that we're going to drop on the cylinder. I'm just going to hide the cylinder for a second, just to show you that this, or hide the box for a second to show you the cylinder. It's hollow. We're going to make that aluminum. And so I'll show that box again. All right, so the solid we're going to leave as structural steel. The cylinder we're going to convert to aluminum and have a 0.1 millimeter wall thickness. So I'm going to go 1e minus 4 meters, or just 1e minus 4. Make sure, check your units. If you've used millimeters before, your defaults may be different in ANSYS. So if it's in millimeters, just put 0.1 millimeters, but here I have 1e minus 4 meters. I'm going to assign the material. Now here is where there's a lot of different options for materials in explicit dynamics and LS-Dyna. I'm just going to use one of the built-in materials. I'm going to search for aluminum alloy and to choose a nonlinear material. But to get more accurate results in a LS-Dyna simulation, I'd need to use a specific material card as outlined in that other video I mentioned. But we're just going to kind of show the capabilities here with this built-in material. Now I'm going to define this floor. I'm going to make that fairly thick to make it rigid. I'm going to make that thickness of 0.1 meter. I'm also going to leave that as structural steel. Now, one thing we got to worry about is where right now it's at the middle of the surface, and so what that'll do is put half the material on top, half the material on bottom, and that's really only important for our case for the contact detection between the cylinder and the floor. So if I leave it as is, the cylinder will want to shoot up because it'll be initially interfering with the floor. So I can show you that if I right-click the mesh, generate mesh, and by default, actually have that setting off, but I go to display, and typically by default it shows the thick mesh. And if I toggle that on and off, I can see that that mesh is interfering because of its thickness with the cylinder. I don't want that, so I want the solid to extend below that surface. So if I go back to my surface definition, this second one, and I switch offset type, you kind of have to use trial and error here, but I know that it's going to be top. It's going to be the right setting. It's either going to be top or bottom. And I can tell that by going back to my mesh and it's on clicking and clicking that thick shells to see that that truly is in the correct direction. I'm going to leave the thick shells, well, I can actually leave that on. That's not going to hurt anything, and it helps me visualize where I'm actually putting the material. And that's, again, that's important for the collision detection in explicit dynamics. Specifically, we've seen in static structural that the default connection type is when surfaces are coincident, it automatically adds a bonded type connection. Here in explicit dynamics, it does not do that. If I wanted bonded, I'd have to add that manually. I don't want any bonded connection. These are all going to be 3 independent bodies. What it does do by default is have body-to-body frictionless interactions, so that when things contact each other, I'm going to drop this block when it contacts the cylinder to detect that collision. Now, normally ANSYS doesn't do that by default, but in LS-Dyna, that's the default setting, because typically you're looking at crash-type events and you want to have that collision detection. So that's on by default. Right now, it's frictionless. We'll see in a second what that does to the simulation. So I have the mesh. I need to add some boundary conditions. I'm just going to fix the boundaries of that plate. Go to the context menu, go to fix support, and grab the perimeter of this. Control click to get more than one. So I'll grab all 4 edges. I'm going to hit apply. So that gives me that boundary condition. Now I need to, one thing I want to do is this block to act under the force of gravity. So it makes it pretty easy for me to do that. It has this inertial block under the context menu. So again, LS-Dyna, make sure I'm on the context menu, go to inertial, and go to standard earth gravity. By default, it's going to want to put it in the minus z direction, but actually I want it in minus y, so I just need to change that. And what that's going to do is apply to all the bodies, apply to gravitational force, acceleration force. It still has a question mark here. I do need to specify the end time for the simulation. Now, as we saw in the theory for explicit dynamics, that the time step is set by the smallest edge length on the element. And so you can see it creates a very uniform mesh. And if I actually look at the mesher, it's using the explicit type mesher to have a strategy of having uniform mesh size. Because we saw when we're doing stress analysis, we actually want small element sizes near stress concentrations to get an accurate stress. But in explicit dynamics, we get penalized by that single smallest mesh. So we usually want a very uniform mesh size in explicit dynamics. Because of that condition, the critical time step, when we go to analysis settings, it has this factor of safety for the critical time step of 0.9. So it's going to go 0.9 times that critical time step to keep the solution stable. I do need to specify end time. Now, typically, like we had talked about for explicit dynamics, because of that small time step, you're usually doing pretty short time duration simulations. We're going to do 0.1 second here. Now it's all set up and should be ready to solve. So I'll hit the solve button. These do solve pretty quickly. We can monitor the solution while we're going by clicking this total deformation under the solution information. It's not going to update automatically unless it's already done simulating, but if we right click and say, as it's running, automatic update, switch to automatic mode, that'll update automatically as it's running. This ran so fast, it's already done. So I hit solution. I'm going to look at total deformation plot. One thing to really look at when you're doing this explicit type simulations is that you want the displacement scale. I'll populate this plot by hitting solve. You want this displacement scale to be 1, otherwise you can get pretty weird looking results. So I'm going to see, if I look at this, you're going to get things that don't look very physically realistic. So if I switch, I want this displacement scale to be 1. Usually for explicit dynamics, you're going to want it to be 1 because that's the actual deformation. So if I hit play here, it's coming down, hitting the cylinder, and it's shooting out to the side. That's because I have a frictionless contact. There's no energy lost in the sliding, which isn't very realistic. So let's add some friction to get it. And we're basically going to add some stuff to the simulation to get it a little more realistic. So let's go to this interaction here. We're going to switch from frictionless to frictional. And we can specify a coefficient of friction. I'm going to do 0.6, which would be fairly typical between steel and aluminum. You can specify a dynamic coefficient of friction that is less than the static coefficient of friction, which would be fairly normal. You do have to put a decay constant in that case. Here I'm just going to simplify the simulation to make those both the same. I'm going to hit solve again and see how that changes the results. Again, I can click this total deformation plot to see the updates as it's simulating, but the simulation does run pretty fast. All right, so I can look at the total deformation plot again, and let's hit play. All right, so it's just coming down, and now because that friction is absorbing some of the energy, the cylinder's not sliding away like it did before, and it's just bouncing up. But let's see if we can kind of increase the forces involved here. Actually, we're not causing enough stress to yield the cylinder yet, so let's increase our force a little bit. So one thing that we can do is set initial conditions. So right now I just had gravity, and when I started simulation, I just let it fall. But I can specify some initial conditions. I can specify initial velocity. But what I'm going to do here is insert drop height. And I also can get to it up here. If I go to initial conditions, click initial conditions here. My context menu will include drop height. So when you do drop height, you have the option of selecting the body that it applies to. Here I need to select a solid body. So I'm going to switch to the solid body selector here just to make sure I get the whole solid body. I'm going to hit apply. and I need to specify a drop height. And so what this allows me to do is I could just have it higher in my model, but then I have to run my simulation over a longer time duration. And because with explicit dynamics, my time set's fixed for stability reasons, that would just add needless time to my simulation. So what I'm going to do is set my drop height here, and what that does, all it does is does the calculation to figure out what the initial velocity for dropping something by 1 meter. So it's really just a convenience. I could enter that initial velocity directly. So we're getting this 4.4, it gives us 4.4 meters per second. We can verify that. So here I have the calculation in engineering paper, and you could do a energy balance to figure out that drop velocity. So if I have the kinetic energy 1/2 mv squared equals mgh, the amount of potential energy, I can solve for v, the velocity. So for that velocity, I get minus 4.4 meters per second, which is precisely what I get here. So it's just solving this equation for you, so you can just enter the drop height and you don't need to do that calculation. And so let's hit solve again now that I have some higher velocity on this structure. Again, I can click the total deformation to see the simulation in progress. So I can see I'm actually starting to crush that cylinder because I have coming with enough velocity where I'm causing it to yield. And so if I look at the total animation here, hit play, and it's crushing that. One thing I can look at here is if I look at the solution information, we get the output of the solver. And that's the one thing I want to point out is we're simulating to 0.1 seconds. That's our current time. This is the time, this is the step, and then it's showing me the delta t. So it's about 6 times 10 to the minus 6. That's 6 microseconds. So time step's pretty small, and it's kind of set by that smallest element size. One thing I want to do is capture a little more detail in that can crushing. So I want to add a little smaller mesh size. I can't go too small or my time step will get really small, but I'm going to add a mesh control here. I'm going to insert a sizing. This is going to be a surface, so I do need to switch to the surface selector here. Select that surface, click apply. I'm going to switch the size to 0.02, so 20 millimeter element size. So make sure if you're in millimeters that you just enter 20. Here I'm in meters, so I'm going to do 0.02. And now if I remesh this, right click the mesh, generate mesh, we'll get a little more detail on that cylinder itself, which will give us a better resolution for that crushing motion. So let me run this simulation again. Click LS-Dyna, click solve. And again, if I look at the solution information, it was 6 microseconds approximately before. It might be a little smaller now. Yeah, since we have the smaller mesh, it's going to decrease the time step size to 2.2 e to the minus 6, so about a third of the time because of that smaller mesh. Let's see if it's updating here as we go. Yep, we see that. And it's bouncing back up after crushing that. And we see it's detecting collision between the block, the floor, and the cylinder, and also the cylinder with itself as you're crushing it, so it gets that self-intersection as well. So let's look at our plot, total deformation plot now. And let's hit animate. And so we get that crushing of that can and a little bit of rebound as that block bounces up. So you can see how this would be very useful for doing crash simulations or drop tests. Look at crumpling, and you can look at how much energy gets absorbed and various metrics like that. All right, so what I want you to do to get credit for this assignment is take a screenshot of your whatever displacement result you received. Doesn't necessarily have to look exactly like this, and upload that to Canvas to get credit for this exercise.